Chapter 15, number 32. Many ray-finned fish adjust their buoyancy by changing the volume of gas in a so-called swim bladder located just below their spine. A. If the volume of the fish increases while the mass remains the same, does the buoyant force on the fish increase, decrease, or remain the same? And B. Calculate the change in the buoyant force on a fish if its volume increases by 11 centimeters cubed, assuming that it swims in seawater. So the very first thing to recognize is in part A, they say, what happens to the buoyant force if the volume increases while the mass remains the same? And it turns out that the relevant part there is that the volume increases, and completely irrelevant is what happens to the mass, because the buoyant force doesn't depend on the mass. The buoyant force depends on the density of the fluid, the acceleration due to gravity, of course, and the volume of displaced fluid. So how much volume has been reduced in the water, how much extra water has been, if you want, excluded. So for us, we can see that since the fish is not going to change the density of the water, then the only thing that matters is the volume. By increasing the volume, the fish has increased the volume of gas, the fish has increased the buoyant force, because more water is excluded from the volume the fish makes up. Part B then says, hey, figure that out. So we'll just put that in here and we'll say, well, we'll need the density of salt water. According to table 15.1 in your textbook on page 503, seawater has a density of 1,025 kilograms per cubic meter. G is, of course, 9.81 meters per second squared. And then the volume, they tell us it increases by 11 centimeters cubed. And then we have to recognize, of course, that we need to convert this to meters. So there is 1 meter per 100 centimeters. But we have to really do that 3 times because there's a centimeters cubed. And so we end up with an increase of 0.1106 newtons. Then we see that we have only, sadly, 2 sig figs, so this becomes an increase of 0.11 newtons.